So today I'm going to talk about unsupervised denoising and why we need unsupervised metrics. I need to acknowledge that this work was supported by NSF, and I acknowledge it very, very happily. This joint work with my postdoc Matan, my student, well, he already left, unfortunately, Adria, and my student Shreyas also left, and our collaborators in Arizona State University. And talking about our collaborators in Arizona State University, the motivation, the scientific motivation for this project was that our collaborators wanted to study catalytic nanoparticles using an electron microscope that you can see here in the picture. This is our collaborator, Josh. And a problem they faced when they wanted to study these catalytic nanoparticles, which is very important to understand because they are essentially everywhere in industry. In like catalysis is necessary in many processes that are very important in different industries. When the images come out of the electron microscope, they look like this. And what we're actually interested in is in a nanoparticle that is actually here. Maybe I should use another color. That is kind of sitting here on a substrate. So I promise you that that's actually what's going on there, but it's obviously very difficult to see from this extremely noisy image. So in order to do scientific analysis of such data, we need to denoise. And something that our applied collaborators keep telling us is, ideally, we would also know how well we are denoising to see if we can trust the results or not. So that's the main scientific motivation for everything I'm going to talk about. This is the plan for the talk. At the beginning, I'll give an introduction on denoising via deep learning. Then I'll talk about recent advances in unsupervised denoising. And finally, I will talk about these unsupervised metrics that enable us to see how well we're doing. All right, so for denoising via deep learning, the canonical problem is that we want to estimate a clean image from noisy, like the same image, but with noise on top. That's the denoising problem. The challenge is that, you know, like setting this up is difficult because there's many pixels. There's at least, you know, like 10,000 or often 1,000,000 pixels in the image. So even doing, for example, a linear regression from pixel to pixel, it wouldn't even be possible. Because of that, we exploit the translation invariant statistics in natural images. Here I'm showing you the covariance for a data set of natural images, where I'm showing you here the covariance between pixel 44 and the rest of the pixels. And you see that the covariance or correlation is very high here, and then it decreases as you go away. That's the actual pixel. And more importantly, this structure is kind of preserved when you shift. Okay, when you look at the covariance between a pixel and the remaining pixels, it's kind of translation invariant. Okay, so this motivates doing something convolutional. You're probably all aware of what a convolutional filter is. We run a filter, the same filter over the whole image, and do a weighted average, in this case, to denoise each pixel if you're using a convolutional filter for denoising. We will just run it over the whole image. Typically, when we do denoising, we use a mean squared error cost function where we want to approximate the clean image. So this would be the output. This would be the output of our denoiser, and we want to approximate the clean image, and a reasonable metric to measure how well we're doing is mean squared error. I say reasonable, but it's not ideal in many ways, but this is mostly what we work with in denoising at the moment. If we just do what I said with a single filter, then what we obtain is a winner filter, which is a linear convolutional denoiser, where the weights are fixed. So we're doing essentially the same weighted average at each pixel. If we don't have a lot of noise, this is just to give some intuition about what we're going to see in a moment, and also, you know, to get a bit of feel for the problem. We don't get a lot of noise. These are the weights that we learn. Can someone tell me what you would expect from, this is the weighted average, right? So this is how we weight each of the pixels to denoise the pixel in the middle. Can someone tell me what you expect to happen as we push up the noise?
You regress to the mean value.
Yeah, but what happens to the weight? Yeah, so we're going to average more, I think is maybe what you're saying, right? So you want to average, like, just to be clear, okay? Here, these are the weights that we're, like, how we're weighting each of the pixels to estimate the pixel in the middle. And this is what happens, the filter that we learn, if we learn a linear filter over all the data in a data set. And now I'm asking what would happen if I push up the noise in all the data set? What is the filter going to look like?
It's going to be sharper.
What's going to happen is you're going to want to average more, is what's going to happen. Okay, so you're going to average more and more because you need to kill more noise. And this is how the winner filter is going to look like. Essentially, you're killing more of the high frequencies because you cannot trust them anymore because there's more noise. If you want to look at this in the frequency domain. And I'm happy that, there's a lot of electrical engineers in the audience, so I can talk about the frequency domain, which I cannot that much when I give this talk to machine learning people. Does this make sense to everyone? And this is just a winner filter, like a convolutional linear filter that we learn over a whole data set with examples of noisy and clean images. And you can show that basically this is equivalent to denoising each Fourier coefficient separately. And when there's more noise, you cannot trust the high frequency Fourier coefficients, so you kill them by averaging more. Hopefully that makes sense. What's the limitations? Of course, we're not going to do this in practice. Well, we can do this in practice, but if the results are going to be not great because we are using the same estimate for each pixel. So in particular, we're going to blur over edges and important features where we shouldn't kind of average on top of them because we're just going to blur them. The image is not going to look sharp. Before deep learning, in particular, when I was doing my PhD, this makes me feel very old. What people were trying to do was to adapt these filters non-linearly so that, like, depending on where you are at, the filter changes and you preserve edges, or alternatively, design and learn sparsifying transfers. So these design wavelets or 2D representations of 2D equivalents of wavelets, or learn some kind of sparsifying transform that was called dictionary learning, and that used to be the state of the art right before deep learning. Nowadays, before saying what we're going to do, what we do nowadays, let me show you what happens when you apply that to our data. So this is the original data. This is a linear convolutional filter, and what happens is that basically the linear filter, the convolutional filter, lets through like the important frequencies, but it completely neglects the edges. So the edges are actually there, I promise you, and bye-bye edges, okay? Because it's only letting through the frequencies where it sees more energy. The wavelet-based filter actually kind of finds the edges, but it's not great. Like, it doesn't really recover the image structure as well. So for our case, these traditional methods don't work that well. So the deep learning solution these days is just to learn a highly overparameterized nonlinear model. And for images, typically a convolutional model. So this is the standard architecture for image denoising, which was introduced in 2017. It's called the DNCNN. Essentially, you have a lot of these filters that I showed you before in each of the layers, but you put rectifying nonlinearities in between to make sure that this is nonlinear and it can adapt to each input, that you don't end up with the same equivalent filter at each point. So how do we do deep learning for image denoising? We gather a data set of natural images or whatever images we're interested in. We add synthetic Gaussian noise to generate noisy images. You can see here the original image, the noise, and the noisy image. And then we train a CNN, maybe to make this clear, that estimates this guy from this guy, okay, over many, many examples. Minimizing the mean squared error that I mentioned before as a cost function. And it works really well, state of the art. It's honestly pretty amazing compared to what we used to have before. It works very, very well in this, like when I say it works very well in this particular setting. Of course, I want to emphasize that this image was not in the test set. You want to test this on images in the training set, sorry. You want to test on images that are not in the training set, of course. So before getting into how this works for the microscope, let's take a look to see at what the network is actually learning. And there's a way where you can actually tease apart a little bit the strategies, the denoising strategies that are learned by the network, which we have found to be very useful in many different settings, which is to look at the gradient of the output pixels with respect to the input image. So what perturbations in the input image would make more of a difference in the output pixels. This is essentially how saliency maps are learned when you apply deep learning to classification. So that would be the analogy, okay? In case you are familiar with that. So here what we're gonna do is we're gonna look at this noisy image, and then we're going to look at, and this is the denoised image, we're going to look at the gradient of each denoised pixel with respect to the input noisy image. Okay, for 3 pixels. We're going to start with this one. So presumably, the important pixels in the denoised image would be around here, right? If we look at this other pixel, the important pixels are going to be around here, and so on and so forth. And that's exactly what we see, okay? So here we see the gradient, again, of this denoised pixel with respect to the input image, and the important stuff that matters for how we're denoising this pixel is exactly around the pixel. Same for the second pixel, which is here, and same for the third pixel. Okay, and now I'm going to show you this when we go to higher noise. So what do you expect to see? Maybe inspired by what we saw for the linear denoiser.
The area gets larger in the same way as before.
Yes, the areas would get larger. If we wanted to, there's a problem here, for example, like when the area gets larger, what's going to happen?
It would average some of the darker pixels instead.
Yeah, so we're going to start blurring over the edges. So what would we hope for if we could, choose the filter ourselves?
That it would extend only in directions where there's similar colors.
Yeah, exactly. So that's actually what happens. If you look at the gradient of the denoised image with respect to input for the neural network understands, is able to preserve edges. So it has learned that this is important to obtain good denoising over the whole data set, and it is able to adapt to produce these adaptive filters, which is what we were trying to, this kind of cool because this is what we were trying to do before deep learning by hand. And this thing learns it in a completely data-driven way. And a way to see that is by looking at these gradients. Are there any questions about that?
Carlos, is it trained on like many levels of noise or one level of noise, meaning you give it like that one level of noisy as the input with the goal being the denoised truth, right?
That's a great answer. That's a great question. Sorry, it's very early in the morning. I usually get a bit later because of my kid. That's a great question. This is trained on many noise levels. We actually have a paper showing that for additive Gaussian noise, the networks do not really generalize well when you change the level of Gaussian noise if you have additive constants in the architecture. If you remove the additive constants from the architecture, then it will actually generalize well across noise levels, but yeah, I didn't include this in this presentation. In this case, yeah, it's trained on different noise levels.
Interesting, thank you.
Any other
how about the type of noise?
This is Gaussian. This is Gaussian. Okay. We're going to look at Poisson noise a little bit later because that's what matters for the electron microscope. And there it's actually low count Poisson noise, so it's very different from Gaussian. Yeah. But here it's Gaussian.
Thanks.
All right. So you can actually apply this to video denoising. This is not completely connected to the rest of the presentation, but it's an example that I find cool, so I like to show it. So in video denoising, we are denoising several frames at the same time. So now if we look at the gradient of a denoised pixel with respect to the input, we're going to have like several frames of input, okay? So let me show you an example. We have a skier that is going down a slope, okay? And here you see that the skier is moving in the frames, right? Because the skier is moving in the video. And now what we're going to do is we're going to look at the gradient of this denoised pixel with respect to the input noise image. So in particular this, with respect to the input noisy image. Here I'm showing you the clean image so that you can see better what is going on, but the input, hopefully it's clear, like to the network, is all noisy. Okay, so now what do you expect to see in the gradient? If you were trying to denoise this thing by doing some averaging, and you want to denoise, maybe I should use this pixel here, what would you do?
Same principle in space and time now.
Yeah, it's the same principle, exactly. And we have something else, which is motion, right? But yeah, it's, if you look at it in time, right? So you want to follow, hopefully that makes sense. You want to follow the skier and average at the same pixel. So you have to kind of understand how the skier is moving, if that makes sense. And we observe that the network actually figures that out. Okay, and it kind of averages at the right places. And if we pull up the noise, we again see the same phenomenon where it averages over more stuff. But it does follow the skier. This is kind of interesting because the network is doing motion compensation without explicitly asking, like training it to do motion compensation. We're only training it for denoising. And in fact, you can use this to try to, so here we have this noisy frame. This is the motion estimates learned from clean videos. Okay, so there's these algorithms to learn how like each point on an object is moving from frame to frame. And we can actually just look at these gradients and figure that out. And it does a reasonable job. So this indicates that the network is actually understanding how the object is moving. Understanding, I mean, again, it learns that it has to track these things in order to denoise well. Completely data-driven.
Can I ask, are you doing convolutions in space and time, or are you using the time along the channel dimension here?
These are only convolutions across space. We only put in 5 frames. It was actually already quite difficult to set up the network. So ideally, you would do something like that. It was already like engineering, like intensive from the engineering point of view to train this thing with 5 frames.
Thanks.
That's an engineering limitation at this point. This is a very good question. Any more questions? Okay, back to the electron microscopy, which is what I should be talking about. Within this framework where you need clean images and noisy images to train your network, this is how we began this project. Well, basically, we had a problem, right? Which we don't have, which is that we don't have the clean images out of the electron microscope, because if we did, what are we doing here, right? This is the whole point. So what we did is we simulated a bunch of images for nanoparticles where we kind of understood the structure that we were expecting. This is not ideal because in many cases you want to use the electron microscope to see what is going on. So you cannot kind of assume, oh, I'm going to have this kind of atom in these configurations and so on. But at least as a proof of principle of what deep learning can do for us in this setting, it makes some sense, and it could make practical sense in certain situations. So what we did is we simulated a lot of possible atomic configurations, and we have, like, there's these quantum simulations that can be done to see what is the image that would come from the electron microscope for those 3D structures. And then we can simulate noise. This part is easier because for the kind of sensor that we're interested in, the noise is pretty well modeled as being IID Poisson with very low count. So like some sensors are not receiving electrons at all, but still the noise is Poisson. And then we pass it through the convolutional neural network and try to denoise. And at first, this didn't work very well. This is the standard architecture. And what we realized is that the standard architectures are very adapted to natural images where you want a very small field of view. Like if you enlarge the field of view for natural images, this makes absolutely no difference, or very, very little difference in terms of PSNR. But in our case, it was killing us because obviously there's a lot of periodicity in the images and you want to exploit that periodicity. So if you use UNet, you need a UNet or something like that, because otherwise you're not going to get a large receptive field without like a number of parameters that wouldn't fit, like we wouldn't be able to use even a GPU for this. So once you use a unit to achieve a very large receptive field, this works very well for this simulated data. If we look at the gradients of the output of the network with respect to the input pixels, we see that indeed the network is exploiting periodicity, but also locally, which is actually something that is pretty difficult to achieve. And this is why these methods outperform what we used to have before. If you are designing transforms kind of by hand, it's actually very difficult to get transforms that are able to exploit both periodicity and locality at the same time. I mean, you can try to do it, of course, but it's not obvious, right? So this is partly why these methods are so effective. And using this technique of looking at the gradient allows you to see that it's actually exploiting periodicity. Any questions up to here? Okay, so this was not very satisfying because, again, we want to actually look at stuff that we don't know is there. So using it to train networks is not ideal. Said otherwise, we often cannot simulate a ground truth because we don't know. This is the whole point of this endeavor. So now remember the supervised mean squared error cost function that we typically use for supervised denoising with neural networks. There's the problem here is that we don't have the clean image to plug in here. So there's a series of very, very, very interesting works that said, okay, so let's do something crazy. How about we put a noisy reference there? So what is the problem with putting a noisy reference there? Like the first time you hear this, you're like, okay, this sounds just crazy. This cannot work. Why can't it work? Can someone tell me?
You have the noise as well, I guess.
Yeah, exactly. You're going to predict the noise, right? You're going to just plug in the noisy image here. You're going to get 0 MSE, and the network is going to be like, I'm so happy, I did perfectly. So the solution to this is to say, well, maybe in some situations we can put in a noisy reference that has independent noise. So it's the same underlying image, but it has independent noise with respect to the image that you put into the network. This sounds a little bit contrived, but we will talk in a moment about how you can bypass the fact that it is a little bit contrived. But hopefully the main idea makes sense. If this noisy reference has noise that is independent with the noise that went into the network, now the network can only approximate the noisy reference by approximating the underlying clean image, because that is what is common between its input and this noisy reference that we're using. That's called noise to noise, and it's a very clever idea. Which is
this related to this deep image prior stuff?
Absolutely, yeah. So in the deep image prior, what do? You actually kind of do this, but you stop training so that you don't overfit.
Yeah, right.
You kind of constrain the network so that it doesn't really get there, and you actually see something that is quite reasonable. Right. The problem with that is that you kind of have to constrain the network because otherwise it's going to just output the noisy image.
Right.
This
well, here, do you need to early stop or?
No, because you cannot overfit the noise if the noise is independent with the input.
Oh, okay.
You might want to early stop for other reasons, but not for that one, because that one, I mean, you might want to early stop because you don't want to overfit the whole noise, like artificially overfit the noise in the training set, but it's not because it's actually seeing the same noise at the input. So it's more difficult to overfit this noise. Let me put it like that.
Okay. And
a comment on that, we typically, when you are doing simulated, when you're using simulated noise for denoising with neural networks, you typically resample the noise so that you cannot really, when you have simulated images, so you cannot overfit it. But anyways, that's a bit of a side comment. Is this idea clear to everyone? So now if we had, which is a big if we had the same clean image, but with independent noise from the one that we're putting into the network, we can do this, and it should work. Of course, the problem here is that we require multiple copies of the clean image with independent noise, which is not obvious to obtain. A neighbor to neighbor is a method that bypasses this issue by saying, okay, how about you do spatial subsampling of your input image, and now you have 4 copies that, of course, are less resolution. So this is not completely ideal and are not identical, but still should be very close as long as the resolution of the original image is decent. And now you can put one of these guys into the network and use another one, for to put in the cost function. Okay, so this is a pretty clever idea to obtain these repeated copies with independent noise. And then another idea is, which is kind of related to this, is trying to implement the same principle. But here what you do is you say, okay, I want to estimate each pixel. I want to estimate each pixel of the noisy image, but I'm going to constrain myself to not use that input pixel. I can only use the rest of the pixels. And if the rest of the pixels have independent noise, again, I'm going to have to kind of learn the underlying image. Here, the key problem is that you're not using the noisy pixel that has the most information about what you want to estimate. These kind of methods are called blind spot denoising. Okay, this is just variations of the same idea, essentially. You want to fit noisy data, and as long as the noisy data has noise that is independent with the noise that is in the input, this should work as a cost function, because the only way you can approximate that is by learning the underlying clean signal. So for electron microscopy, this is the noisy data. This is a reference that in this case, we can obtain by a lot of temporal averaging, because this nanoparticle was very stable, which is not typically the case. So just in case you're wondering where does this reference come from. This is what happens for the supervised method. And here, this is not going to be obvious to you, but let me tell you a story. Like, we were very happy with this supervised result, and then we showed this to our collaborators, and they were not happy, because they said that here in the actual, let me get this right, in the actual reference, you see kind of a pattern here that is very important, and here the dominating pattern seems to be like this. Okay, so they weren't happy about that. And the reason is that this guy was probably overfitting the kind of patterns that we had put in the trainings. This was not obvious to us at all, but it was very obvious to our collaborators. So then we applied this unsupervised method, and the unsupervised method was much better at recovering this kind of stuff that you see in that direction. The problem with the unsupervised method is that we didn't have a lot of data to train the unsupervised method. So it actually failed at finding, for example, some of the atoms on the surface, because we didn't have enough data to train it. So motivated by this, we developed an approach where we pre-trained a network with the supervised data, and then we actually fine-tuned it on the actual noisy image, on the same noisy image that we were interested in. That is very little noisy data, so it's very easy to overfit. The way we avoided overfitting was by just updating the gain parameters in the network. Okay, if you're familiar with batch normalization, if you just update the batch normalization parameters, then you don't overfit, and you're able to kind of fine-tune your network well. And we call this method gain tuning. And here we get the best of both worlds. We get like a better pattern here that our collaborators were happy with, and we also get to find the atoms that were on the surface of the nanoparticle. So this is a semi-supervised method, if you want, that tries to combine the best of both worlds, like having a lot of simulated data and then being able to fine-tune, or in this case, gain tune, because we're only updating the gains on the noisy data. Any questions about this? Sure.
With fine-tuning, what would be the fine-tuned data set? Is that you fine-tune? We
use the noisy image to fine-tune, but the problem, like, if you have to be very careful to avoid overfitting, right? Because you're using the same data that you want to denoise. So this is why we only update the gains. And surprisingly, this does not produce overfitting, like basically every example we've tried. Of course, there could be other. So this basically, the general principle is you can actually use your noisy data to fine-tune your network, but you have to be very careful about overfitting. So you have to constrain the fine-tuning process. And we found that the gains is a good strategy, but there may be others.
That's it. Yeah. Thanks.
Any more questions? Okay, so we finally arrive at unsupervised metrics, which is kind of the point of this talk. When you look at previous works on unsupervised denoising, unsupervised methods are typically evaluated on simulated data with known clean images by visual inspection when you actually apply them on real data, or by comparing them to clean images estimated via averaging. This was the reference that I just showed you. So you average a lot of images to kill the noise, and you call that like the clean version. This is extremely difficult to obtain for real data. You have to kind of put a camera that stays there and takes many, many frames. Or in the case of the microscope, you have to hope that whatever you're imaging does not move underneath. Okay, so basically this is to show you that there was this challenge about how to even evaluate these methods in precisely the settings that you're probably going to care more about, where you don't have clean images available. So it would be very nice to have some kind of metric for quantitative evaluation that doesn't require clean data. In particular, again, the motivation is that my collaborators kept saying like, yeah, sure, but how do I trust what's coming out of this thing? So if we look at this noise-to-noise cost function, where we have the denoised image and the noisy reference, we could say, well, you know, if this is working for training a network, how about we use it to actually evaluate, you know, evaluate how well the network is denoised. There's a little problem with that. So let's find a little problem. So here, imagine that we just have additive Gaussian noise with fixed variance. This can be applied to Gaussian noise with different variances. This can also be applied to Poisson, but it can be applied in more generality, but just to fix ideas, okay? So we have this clean image X, and then the data is equal to X plus C, where C is the noise, and the denoised estimate is F of Y, okay? So now the MSE that we want, we would love to have this. We would love to be able to compare each pixel of the denoised estimate to the clean image, take the squares, sum them up, do the average, and that's the MSE. We would like to have this, okay? But unfortunately, having this requires having the clean image, which we do not have. This is the whole problem. So what we're saying in this noise-to-noise business is that we have a noisy reference A that corresponds to the same image, and but has a different noise realization on top. This is what I meant by saying that the noise in what is going into the network, which is this guy, is independent from the noise that is going into the cost function. Okay. So now, if we compare A and F of Y, which is how we're training these unsupervised methods, now we're not training anymore. We're just trying to determine what is this MSE. Okay. We assume that the network is trained with some other data. So what's the problem here? The problem is that when we expand A, we have this Xi plus Wi. If we only had this guy, we would be very happy because we would be able to estimate the MSE. But this guy is there, right? And if we expand this and assume that, you know, the noise is independent with everything else, we get a term that is exactly equal to the MSE that we want, but we get an additional term that is basically the variance of the noise, which is not surprising because, again, like, you know, you think about this guy is the clean signal and also the noise. And because the noise is independent with everything else, in the end, the variance comes out on its own. Okay, so we have something that is approximately equal to the MSE, but crucially, it has this term, which is the variance of the noise. So this suggests doing what? Doing a correction to this cost function in order to make it an estimator of the MSE. What do we need to do in the correction? We need to eliminate the noise. We need to kind of subtract this guy. Of course, for Gaussian noise with fixed variance, this is easy to do. You just estimate the variance, you subtract it, you're done. But there's many situations, like, for example, low count Poisson noise, where that would not work. So what do you do in those cases? Well, what you can do, and this is, I mean, I'm going to explain this for the Gaussian noise, but we can prove that this works also for IID Poisson noise. What you can do is you can say, okay, let me gather two additional references that also have independent noise. And what I'm going to do is I'm going to try to subtract an estimator of this guy, which is obtained by canceling out the clean image in the additional noisy references. And then, okay, you have to divide by 2, right? Because you have 2 clean images. And this is going to give you an estimator of sigma squared, okay? Just to show you that because of independence and so on, this splits like this and you get sigma squared. Again, this little proof holds for constant Gaussian noise with constant variance, but you can also prove something very similar for Poisson noise. Basically, you need the noise to be independent, pixel-wise independent, and then you're fine. So this is what we call the unsupervised MSE. You take the difference with the noise, a noisy reference, and then you correct to make sure that you do get an estimator of the MSE. If you don't correct, you can still train a network with this thing because the network doesn't care about this part. But if you want to know how well you're denoising, you need to correct. That's the take home here. Okay, just a picture. Here we're comparing the denoised image with a noisy reference, and then we have this extra term that corrects for the fact that we're comparing to a noisy reference. We're not comparing to the clean image. Okay, hopefully that makes sense. If you want to obtain the PSNR from this, it's, we use the usual formula, which this is how people compute the PSNR from MSE in image denoising. We just plug in the UMSE instead. I'm not going to go through the details, but you can actually prove that if the noisy references correspond to the same clean image and the noise is pixel-wise independent, the UMSE and UPSNR are an unbiased estimators of the MSE and the PSNR. They are consistent. You get convergence in probability. And the UMSE is asymptotically Gaussian, which could enable you to, for example, have confidence intervals if you want. This is just some simulations where we do know the clean images. So in particular, we know the actual MSE. And then we repeat this process over and over the noisy references to see the distribution of our estimator. And we see that the estimator is indeed approximately Gaussian, and that the variance of the Gaussian goes down as we include more and more pixels. So here the asymptotics is in terms of the number of pixels. And this is important. Okay, it's not in terms of the noisy images that you're using or anything like that. Here, the asymptotics is just how many noisy pixels you have. If you have more noisy pixels, this is going to converge. Okay. Of course, under the assumptions that the noisy references correspond to the same clean image and the noise is pixel-wise independent, which are approximately true for our application, and I would say a few other applications, but it would, it would be very interesting to extend this beyond. You can compute confidence intervals because of this Gaussian assumption. Here we're showing that some of confidence intervals on our simulated data actually are confidence intervals, which is kind of nice. Let's go back, because you might say, well, wait a minute, but you said that there's already an approach to kind of do this by just averaging noisy images. The problem with averaging noisy images is that that's also going to be consistent in the sense that in the limit when you have many noisy images, this is going to converge to the clean image, but you need many noisy images. Our consistency is for the same image with respect to the pixels. So here, we would require many noisy images to converge to a true MSE because we're not canceling out the noise efficiently enough. Okay, and here you see this in an example where we try to get the same precision as we get with the UMSE. The UMSE is using 3 noisy images. And in order to just average noisy images and get the same precision, you need like thousands of noisy images. So this is not going to, this is not very surprising because you're not explicitly canceling out the noise. So in order to average the noise out, you have this square root of n dependence that is what it is. Hopefully that makes sense. So now you might be saying, okay, this sounds great, but where do I get these noisy references? I mean, this is really the key question. And at the moment, we have tried out 2 things that, make some sense. One is spatial subsampling, where you do this trick that was in the neighbor-to-neighbor denoising algorithm, and you just kind of subsample a high-resolution image into lower-resolution images. And those are approximate copies of each other, but not exactly. And we'll come back to this point in a moment. Here I'm showing you the difference for this case. And for videos, you can use consecutive frames. And this actually works quite well for the microscope data. Okay. But again, the problem is that if this guy is moving very fast, then you're going to have a problem, because in consecutive frames, you're not going to have exactly the same underlying clean image. This spatial subsampling can introduce a bias if your images are not high resolution enough, they're not smooth enough. If they're not smooth enough, then adjacent pixels are not very, very close to each other. So when you do this spatial subsampling, you get systematic differences, and we actually see that here for these natural images that, again, are not like super smooth because they're not very high resolution. So this is why we're seeing this bias between the MSE and the UMSE values when we sample many UMSE values by sampling pixels. If you do this for electron microscopy, the bias is much smaller because the images are much higher resolution and they're also much smoother. But this is definitely a problem in practice, and it's a challenge for future work. Here I'm just showing you some results. This is the PSNR for some Gaussian noise and natural images if we compute it with the actual clean images. And this is what happens if we approximate it using the UPSNR only from noisy images. Okay, the estimate is really good. But here we're using the actual true noisy images, not true noisy images. What I mean is we're using replicas of the noisy image that have independent noise. So there's the same underlying clean image, which is difficult to achieve in practice. This is with spatial subsampling, where you start seeing that the approximation is not as good because of this bias. But still, if the alternative is nothing, or the alternative is just averaging many images, which is thousands of images, which is completely impractical, at least this gets you somewhere, right? This gets you in the ballpark of the PSNR. But you do get this bias if you rely on spatial subsampling. For electron microscopy, this is for just different, I forgot to say that, this is just different denoising algorithms. We again see that the PSNR, the UPSNR is a really, really good estimate of the PSNR. If you rely on spatial subsampling, the estimate is actually still very good because of what we saw. The bias here is much lower for this kind of images. But there is this limitation, right? Like if your noisy replicas might not correspond to exactly the same underlying clean image, then you're going to get some bias. In the real electron microscope data, just to tell you a bit of a story, we encountered an issue, which was that this is the correlation of each pixel with surrounding pixels. So with itself, the correlation is 1, obviously. But actually, the correlation with the pixels just beside it was non-negligible because of some issues with the sensor. Something about how the electrons are dimmed or something like that, which I don't completely understand. So in order to avoid this and make sure that the noise was actually as uncorrelated as possible, we had to do like more spatial subsampling to ensure that the noise was uncorrelated. So this is just to show you that in reality, the noise being uncorrelated is also a problem. It's also a challenge. This is often just assumed in papers, but often the noise is not completely uncorrelated. I'm not showing this here, but we have since found out that if we do temporal subsampling, it makes our life easier. There's less correlation. Okay, so for the microscope data, that's probably a better idea, which goes to show that if you're going to apply unsupervised methods for denoising that rely on these independence assumptions, a very important thing at the beginning of, before doing absolutely anything else, is doing a study of the noise properties. Okay, so for the real electron microscope data, here I'm zooming in just so that you see how this low count Poisson noise looks like. So a lot of the pixels are just empty. It's kind of crazy, actually, how noisy these images are. I'm just going to show you some results. This is what happens if we just do Gaussian smoothing. So the denoising is pretty terrible. The UPSNR tells us that the denoising is not great, although we are capturing kind of like the high level structure of the image. The unsupervised denoisers actually work very well on this data, and the UPSNR indicates that that's the case. Okay, just to show you again, I mean, it's quite incredible how from that you get this kind of estimates. This is again like a nanoparticle. You see the edge of the nanoparticle here. Okay, so the conclusion is that UMSE, this unsupervised version of MSE and PSNR are consistent estimators of MSE and PSNR, but there are some open questions that we don't really know how to resolve very well, which is how to address spatial subsampling bias if you want to use just a single image. And if you just use a single image, you have to do this subsampling because you need noisy replicas with independent noise. And then the problem there is that you're kind of breaking up the underlying clean image in a way that might not preserve identical copies. So then you get this bias that we observe. How to deal with correlated noise, this is a big one. An interesting idea is that noise, and at least in the applications that we are more familiar with, tends to have some spatial correlation. So you might want to constrain this in a way where, you know, you're like not using just like not, for example, you could do more aggressive spatial subsampling or something like that. What is the problem? You go back to this bias issue. So there's this kind of like, there's this problem. And then, of course, it will be very interesting to extend this to inverse problems beyond denoising. It's not difficult to think how you might extend it to compressed sensing, where you have highly incoherent random measurements. Beyond that, I don't know. That does sound quite difficult. And these are the papers if you want to take a look. And that's it. That's all I have.
Thanks, Carol, for the great talk. Any questions? So I have a question. So I mean, for this like a supervised metric, so can you also utilize this for like a deep replier to deliver criteria for early stopping? Because I mean,
for early stopping, you can just use the uncorrected cost function. And in fact, yeah, like you probably should. In not only for deep image prior, you like when we were applying the unsupervised denoising method, we found that doing good early stopping makes a huge difference. And this is something that was not reported in the literature before, maybe because of the kind of images they were focused on. But for that, you can just use the cost function without correcting, because you know the correction term is just going to stay the same. You know, I mean, like you can just see when things start going up, you don't need to correct for that. But your intuition is right that you can use this kind of unsupervised cost functions for early stopping, and you should.
I see. Any other questions from the audience?
Could you clarify, are you proposing to use this unsupervised mean squared error for both training and for, you know, evaluation at testing time, or mainly the latter?
The latter. In training, it doesn't matter.
Yeah, okay. All right, that's...
In training, it doesn't matter at all, because this extra term is you're not like differentiating.
Right, yeah, exactly. Well, yeah. And I'm reminded of the discrepancy principle for choosing regularization parameters. If you try to use it at training, it seems like the first term would be underestimating the mean squared error. So okay, I definitely just want to make sure I understood that it's mainly at evaluation.
It's only for evaluation. So this comes from the fact that, you know, you do this, like there's all this literature on unsupervised methods, but then you want to apply them in practice, and your collaborator tells you, sure, but now how do I evaluate this thing? And it's very unsatisfying to tell them, well, I need some ground truth data to compare to, because they're like, yeah, okay, so why did we do this whole thing? So what we're trying to push towards is having some kind of unsupervised method, which of course is going to have flaws and limitations, but nevertheless, in practice, that's all we have. So.
Great, thank you for the super interesting talk.
Ching, if I have time for one more question. I don't know how to raise hand, actually. So on the Zoom. So this is self-supervised denoising method seems very compelling. And I especially intrigued by the neighbor-to-neighbor idea. And I wonder how that idea, or noise-to-noise, or neighbor-to-neighbor idea can be applied when there are missing data in the image, the data that you don't have samples with.
What kind of missing data? Like missing pixels altogether?
Missing pixels, yes.
Are they missing completely at random?
They're missing means that there's no
no, I know.
samples. Okay.
But
right.
if they're
No.
missing at random, you're not so far from our low count Poisson noise, because like in our data, we have missing data because basically the Poisson noise is so low count that when you see black here, it's just that there's no electrons in the sensor. So that's a 0. So but the missingness is like follows a Poisson distribution, if that makes sense. When the Poisson distribution is 0, there's no sample there. So in this case, it works. In
Okay.
your case, it might depend on how the pixels are missing. And then we would have to see whether the assumptions underlying the cost function actually hold.
Right. So, but many of the matrix that you showed are based on the Gaussian noise, additive Gaussian noise.
Oh, this was just the proof that what I showed works for
I see.
IID Poisson.
Okay, wonderful. Thank you.
But I also don't want to oversell this. IID Poisson, so you need pixel-wise independence.
I see.
That you need. Without that, everything falls apart. The Gaussian assumption was just kind of like show a very simple proof. It's not that the other proofs are more complicated, it's just the notation is a little bit more complicated. But IID Poisson is fine, but you need pixel-wise independence.
Okay, great.
There's another question from the chat. So Matt is asking, do you need to take the atom's thermal noise into account? Does that affect the image of the atom that's being captured?
Yeah, I'm not sure. Here, I'm going to just reveal my ignorance. I'm not sure exactly. So I know that this is shot noise. I think they're like here thermal noise is not an issue, I think, but I'm not sure. In any case, the actual noise model is not important, but what is very important is whether there are correlations in the noise from pixel to pixel. So a good, like a very like practical property of these algorithms is that they don't assume a noise distribution, again, as long as the noise is uncorrelated from pixel to pixel. And now you might be wondering, okay, wait a minute, you're using MSE, which kind of suggests that you have like a Gaussian distribution, right? Because it's the likelihood of it's a Gaussian likelihood at the end of the day. Well, if you modify this to use Poisson likelihood, we have seen over and over that it just makes no difference, which is kind of frustrating, right? When you're trying to do things the right way and so on. MSE does just as well. And the reason we think this is just because of the high nonlinearity of the network that kind of accounts for that already. And by doing well on MSE, you end up doing well on the Poisson noise. But that's by the way another open question: how to design cost functions that are maybe better adapted to the noise, or if I can ask about for anything that also capture more like the information that we really care about, which MSE not always does. But anyways, there I diverged a bit from your question. So not sure about the thermal noise, just to come back to your question.
Okay, any other questions? If no questions, thank the speaker again. Thanks, Carlos.
Yeah, thank you.
Bye, everyone.
Thank you very much.
Thank you everyone for inviting me.